Hello everyone. Today we'll be discussing about the Kruskal's algorithm for finding the minimum spanning tree. Previously we had discussed about the Bellman-Ford algorithm as well as the Dijkstra's algorithm. So today we'll be discussing about the Kruskal's algorithm for finding the minimum spanning tree, nothing but MST. So the approach is, let's consider this step by step. Let's go step by step. First, the approach is Kruskal's algorithms is based on the greedy algorithm. So if you don't know greedy algorithm, I have considered the problem and I have explained the greedy algorithm. Please do go through this one so you will understand this one better. So Kruskal's algorithm is a greedy algorithm. Basically, it is used to find the minimum spanning tree, MST of connected or the unconnected graph, connected or unconnected graph. So if we have to find the minimum spanning tree of a connected or the unconnected graph, then we can make use of the Kruskal's algorithm. Basically, it is a greedy algorithm. So let's consider the steps, right? Let's consider the approach, and then we will be implementing that one in the code along with the example. Finally, we'll discuss about the time complexity and the space complexity of the written code. So the main steps are, first what we will do, we will sort all the edges in the non-decreasing order of their weight. So the main step is here in the Kruskal's algorithm. First we will sort all the edges in non-decreasing order of their weights, right? So this is not necessary. Non-decreasing order of their weights. So after sorting all the edges in non-decreasing order of their weights, we will pick the smallest edge. So here in the step 3, we will pick the smallest edge or the small edge, and then we will check if it forms a cycle. So we will check this one whether it forms a cycle. Whether it forms a cycle with the spanning tree formed so far using the union find. So here for this one, we'll be making use of union find, right? So by making use of the union find, we will check if the smallest edge forms a cycle with the spanning tree that is formed so far. If it doesn't form a cycle, then we will be adding the smallest edge to the minimum spanning tree. I hope this is completely clear. So this is the main step actually, basically. So I hope this is clear. So finally, after this one, what we will do, we will repeat the same process until we have v-1 edges in the vertices. Is nothing but until we have v-1 edges. I mean this one is represented by v-1, right? So we will repeat the process until we have v-1 edges in the MST, right? So I hope this is completely clear. So this is this approach that we will be going with. Let's start writing the code and let's discuss this code with the example, and let's finally discuss the time complexity and the space complexity. I'll just give here function. This will be, let me take Kruskal vertices v edges. I'll consider edges itself. So I'll just make use of the helper function to find the root of the node with path compression. So I'll just give here function. Let me give find here. So this will be let me consider parent as well as the node. So here we have to find the root of the node with the path compression, right? So I'll just consider parent as well as instead of the node, let me consider here I. So I hope this is clear. Next step is we will recursively find the parent and perform the path compression for the efficiency. If I can write in this way, parent of I, if it is not equal to I, then we will recursively find the parent and perform path compression for the efficiency. We have to find the parent, right? So first let me write this one here, parent of I. Let's make use of the recursive function find we have made use of, right? So with the parameters parent as well as the parent of I. So I hope this is clear. Finally, what we will do, we will return the root of the subset, nothing but the parent of I here. This one I'll just consider here parent of I. So I hope this is clear. After this step, we will make use of one more helper function to union two subsets by the rank. I'll just give in this way function. Let me consider the function name as union itself. We have to go with parent rank we need along with x and y. So these are the parameters I'll be going with. First, let's find the root of x, and then we will find the root of x and y here. So I'll just give here root x equals, we already have the, we will make use of the recursive function find. So the parameters are parent as well as x. Same thing, let me copy, and for the y as well, make the necessary changes, right? Just copy this one and make the necessary changes. So this one will be parent y. So I hope this is clear. So next step is, let's attach smaller rank tree under root of the higher rank tree. So I can write in this way. We can just make use of the this one, right? What do you call if condition here? If it is not equal to root x equals not equal to root y, then again I'll just make use of the if condition here. What we have to do? We have to attach the smaller rank tree under root of the higher rank tree, right? So I can write in this way, I think. Just give me a second here. For rank of root x, this one is greater than rank of this one root y. Then finally, what can I do? Root x becomes the parent of root y. So here I can just give parent of root y. This one will be root x itself. So I can just give here root x. So I hope this is clear. Else, so here root y becomes the parent of root x, right? In this way, if rank of root x is less than rank of root y. So I can just copy the same thing here. Let me copy the same thing here and make the necessary changes here. So this one has to be here. Sorry, this is fine. Rank of root x here, if it is lesser than the root y, then root x here. This one will go root y. So finally, after this, what we will do? Just give me a second here. We'll go for the else part. Else, if the ranks are equal, then we will make a root x parent and we will increase its rank. So here, this will be root y equals root x, I can say, and finally rank of root x. Let's increment this one. So I hope this is clear. So finally, what we will do, we have to, this is it for the this one. What do we call? We have function union basically. Next, let's sort the edges based on the weight, nothing but the non-decreasing order. So here it has to be edges sort non-decreasing order. So here I have to give a of 2 minus p of. So after this, let's initialize the parent and let's rank the arrays. I can just give here in this way. Array plot from, so this one length will be length of v. Also this is 2D array, right? So I'll just consider in this way here. Let me consider some random underscore here. I hope this makes sense. So here we are just checking that each node is initially its own parent right here. So that's what we are doing here. Next, we will check whether all nodes initially have a rank of 0. So let me give here const rank equals array dot from. Let me give the length of v here. Finally, let's go with 0. After this step, we have to declare the array to store the edges of the minimum spanning tree as well. That's what we are doing here. So let me give here mst equals this one. I hope this is clear. Finally, we will iterate through the each edge in the sorted list. For this one, I'll just give for let u, v and w, nothing but the weight I have considered. Weight of edges here. First, let's find the roots of the nodes u and v. This is condition. I'll just go with, we already have the find function, right? We can make recursive call here. Parent as well as the u I'll be considering here. If it is not equal to find of parent comma v here, then if they belong to the different sets, then this edge doesn't form a cycle, right? So we will add this particular edge to the minimum spanning tree. I can just, for adding, I'll just make use of the push. I can write in this way. Minimum spanning tree dot push of here. This will be within the array. So I'll just make use of u, v and finally weight. So I hope this is clear. After adding the edge to the minimum spanning tree, let's make use of the union function for union of the sets of u and v to form one set. I'll just be making use of union function here. Parameters will be parent, rank, u and v. I hope this is clear. So finally, we have to return the edges of the minimum spanning tree. So that's what we'll be doing here, right? MST. So I had missed on braces here, there. So this is fine. Here actually, when I copied this one right here, else if. So I copied only this thing. Actually, I had missed one bracket here. So that's what I wrote this one right at the end. So I hope this is. So let's check this one with the example. I'll just copy paste the example here. So that here, let's check whether this works correctly or not. So let me hit this one, run. So here what we are getting, unexpected token dot here at line number 10, right? So I'll just remove this one. So yeah, you can clearly see here, minimum spanning tree, MST, edge 2 to 3, we are getting weight 4. This one, edge 0 to 3, weight 5, as well as edge 0 to 1, weight 10. So here we are getting the output correct. So this code works absolutely correct. So next, let's discuss about the time complexity and the space complexity, right? So the time complexity, overall time complexity would be big O of E log E, where we know that E is nothing but the number of edges, and the space complexity would be big O of V plus E. Why big O of V plus E? Because we are storing the parent rank arrays as well as the minimum spanning tree edges, nothing but MST edges, right? So the overall space complexity would be big O of V plus E. So yep, this is it. This code actually, I had explained everything that I know, and also we have checked this one with the example. The example also works correctly. So finally, we have discussed about the time complexity and the space complexity. So I hope this is completely clear. So this is it. Thanks for watching, guys.